Bismillahirrahmanirrahim. Assalamualaikum. Hi, how are you everyone? Today we are going to be taking lecture number 17, and this is process modeling and simulation CHENG324, and I hope that you're going to gain some new information today. And as we have finished from last time, we have taken the types of inputs and their effect on the output if we are dealing with a process of a first order process. And today we are going to take like two additional processes. The first one is the integrating process, and here the integrating process is, so we said there's a first order process, there's a second order process, there's a third order process, and there's something also called the integrating process. Okay, so the integrating process says that the relationship between the output and input is an integrating process. And what is an integrating process? It is something like if you have a change in the input, if you have the change in the valve input, the height is going to increase. However, it's going to increase, and it will never stop. It's like an integrating process that it increases and never stop. And actually, if you look at it, that if you had a step input of U of S, okay, step input which is M over S, as we have said before, and it's written here, M over S. So what you will have? You will have Y of S is equal to M over S multiplied by the integrating process, which is K over S. So you will have Km over S square, and that is Km over S square. You can see it? Yep. And if you take the Laplace inverse, and taking the Laplace inverse here will give you Kmt as 1 over S square. The Laplace inverse of 1 over S square is T. And what is T? It's T just tells you that this Y will just increase in a T manner. T manner, that means it will increase like that. So increasing like that, that is it's integrating, it will never reach a steady state, new steady state value. And this is true. Just substitute T is equal to infinity here, you will know that it will never, it will go to infinity. And not only that, even if you use the final value theorem, which is limit S approaches 0 for S, this is the final value theorem, Sy of S, this will be S multiplied by Km over S square. You will cancel one S, S is equal to 0, so anything divided by 0, so this will be going to infinity. So we know that definitely that there's no final value here, there's no final value. Why there's no final value? Because it goes to infinity. Okay, so the integrating process is just a kind of a process that you should consider, because if you have an integrating process, you're going to have troubles of how you're going to deal with the system. Okay, an example of an integrating process is if you have a pump rather than a valve at the output. Okay, and this will need some kind of explanation. So what happens here if we have a change in the input? Okay, so this input goes from, I'm not talking about now flow rate, I'm just saying that if I open the valve from 20 to 30%, so definitely the flow rate is going to increase, right? So if the flow rate increases, what happens usually is that if we had a valve at the output, here, what happens is that the higher the head pressure, the more liquid that will go out here, and the lower the head pressure, the lower it will come out here. And this is what the example that we were talking about, the Vimto, I don't know if you can remember that example. And we said that the first person comes and takes from this this pot here, and he gets his first cup. You have a very high flow rate getting in, but the last guy, when he comes and it's a very low head, he need to lean this whole bucket, so that he can get some liquid out. Okay, so what I'm trying to say here, the higher the head pressure, the more that you're going to have the flow rate. Similarly for the tank that you are sitting up on your home. Why you're keeping it at the top? You're keeping it at the top because you can have a head pressure, and because of the head pressure you can have your water coming out at a good flow rate, acceptable flow rate from your tap water, and so on. But by the way, now all of our tanks that are sitting on, or most of our tanks that are sitting up there in the, over the roof, they have a pump as the output. They have the pump as the output. And because they have a pump, what happens is that it is because there's no input, and this input comes from the government to our tank, and usually it goes to the tank which is at the bottom, and then you push your water from the bottom till the tank at the top. So what you're saying that because you had no input, so in other way around, you had your input was less to 20%. And what happens if your input is less? If this was a valve, if the head pressure drops down, the valve is going to do nothing, but the flow rate is going to be less. Why? Because the flow rate, output flow rate, depends on what? Depends on the characteristics of the valve and the liquid, and it depends on the height. But talking about a pump, definitely it does not depend on the height. Pump just pumps with a constant flow rate. And what happens when you have your tank is what happens at your home? Sometimes it is pumping really very strong, really very high flow rate at a constant flow rate, and then there's nothing, there's no water at all. Why? Because your tank up on your roof is empty. Why did the pump did not realize that it was empty? The pump does nothing, it just pumps out. So this is called an integrating process. If you have an increase, the pump is not going to take any action. If you have a decrease, it doesn't take any action. Okay, how can we represent this in terms of our system here? How we can represent this in our terms of our system here? And to represent this, I think it's a good idea to represent this. Oh, that's a beautiful picture from last time, huh? Okay, so that was a beautiful picture we had from last time, and I think that you already recorded that, right? And so what you're going to have a new board, and we are saying that we have a tank here. So we do have a tank, and I think so this should be like that. Okay, so we have a tank, and within this tank we have a pump here, and of course we have an input flow rate, and we want to see how the height changes with time. So how do we do this? We form the overall balance dm by dt is equal to mn minus m out. Okay, and then we know that this m is equal to rho a into v, so it will be rho a into dh by dt, which is equal to rho n fn minus rho f. And of course we cancel out the densities, so our problem goes down to dh by dt is equal to fn over a minus f over a. Now for this process here, remember we substituted f is equal to alpha square root of h. I think you already remember that equation, but that is if we have a valve. Whereas if we have a pump, f is just f. Okay, it's just f. It is a constant flow rate that we put in. So here f is just f, it does not change. And now if you want to work on the system to get our transfer function, if remember what we should do? We should write our equation in the linearized and deviation format, and we do this by writing dh prime by dt is equal to, it has a function of what? It has a function of the state variable, which is the differential equation, and the inputs. In this case, what do I have in input? I have my fi as an input. Actually, I also could include f if I want. Okay, I also could include f if I want to include it as a changing input. So we'll just keep it like that. And this is my function. Okay, this is my function here. So let's start our process. So dh prime by dt is equal to the partial differential with h into h prime plus the partial differential with fi into fi prime. And by doing this, And by doing this, what do we have here? df by dh. This is my function here. Okay, so this is my function here. So what I'm trying to do, df by dh. df by dh, oh my god, there's no h. There's no h here. Okay, and f is not a function of h. fi is not a function of h, so there's no h. So simply, the first term is going to be, the first term that I have is 0. Plus df by dfi, which is 1 over a. So that's 1 over a into fi prime. So my equation is just like that. dh prime by dt is equal to 1 over a into fi prime. Now, taking Laplace, so I apply Laplace now. I apply Laplace. Okay, and I just want to write here that I have applied the linearization plus deviation steps. Okay, putting it in a deviation format. So now I have applying the Laplace transform. When I apply the Laplace transform, I have the differential equation will be s into h prime of s is equal to 1 over a, and this will be fi and the s domain. And now I divide h prime into fi in the s domain is equal to 1 over as. And you already got it, right? You already got it. We didn't have this s plus 1 as you usually have. And that s plus 1 over s plus 1 is an exponential term that goes to a new steady state value. But in this case, this is an integrating process. Okay, this is an integrating process. And now you know that we could have an integrating process if we have a pump at an exit. And this is our function here. So going to our problem in chapter 4. So this is what we have. Okay, so this is what we have. And this is our system where we got h prime over qi prime. In this I used fi. Over fi is equal to what? Is equal to 1 over as. 1 over as. And this is what we obtained. Okay, that's great. So that is for the integrating process. That is for the integrating process. Now, what we want to study, we want to study if we have a step input to a second order process. Okay, so a second order system. If we have a step input to a second order system, what will be my response? Okay, so we are going to look into our response in a moment. And actually, to study this response, we are going to get to some new terminologies that we need to get used to. So to start with, this is the standard form of my second order system. But I need to build this with you step by step. And I'm going to start this building it step by step by taking two tanks in series, just to get the idea of how a second order process is built. And then we can go to find out how is the standard form developed for us. Okay, so this is what I have. This is what I have as a 2-tank system in series. So this is like fi, and this is like f1, and that is f2. And I would say that there's fi in, and because of fi I have a certain concentration here. Of course, I'm having a mixture here, and I have, for the first tank, I have tank 1 and tank 2. So what do I have here? I have also Ca, okay, Ca1, and I have Ca2, and if I want to find the equations, I mean, I'm not going to go through the math now, but if I want to find the equation, I can find the equation of Ca over Fi, and I'm going to see that it will obey a first order process. And we have done this before, okay? We have done that before, so I'm not going to go through it again. And if you want to find the relation of Ca2 with Cai, I cannot find with Cai. I can find with Ca1. I can find the relationship with Ca1. And for Ca2 with Ca1, we will also discover that it will be a first order process. Okay, So we can see that we have a first order process for CA1 to Fi, and another first order process for CA2 to CA1. However, if I want to find the relationship for CA2 to Fi, that means how does this concentration change due to the change in Fi and not CA1? Of course, we know that if Fi changes, CA1 will change, and eventually CA2 will also be changing. So how to find the relationship between CA2 and Fi? And this is what we're going to do. We are going to say that CA2 over Fi, we simply can multiply those two transfer functions in series. As we said, it's like we are having two blocks. This is Fi, and this is CA1, and this is CA2, and this is the relationship between CA2 and CA1 and Fi. CA1 and Fi, the relationship is K1 over tau 1s plus 1, and the relationship that I have for CA2 to CA1 is K2 over tau 2s plus 1. And if I want to find the relationship between CA2 and Fi, I multiply these two transfer functions. So what I'm going to do here, I'm going to multiply these two transfer functions, which is CA2 over CA1 into CA1 over Fi. And actually it looks like, it's not that I'm doing this, it looks like that I am cancelling this term with this term here, and I'm getting CA2 over Fi. And of course we are not really cancelling them, we are multiplying those two transfer functions. And we will get CA2 over Fi. And what will be my equation here? It will be K1 over tau 1s plus 1 into K2 over tau 2s plus 1. So that is my equation. Multiply them. We will have K1 into K2, so two constants, over tau 1s plus 1 into tau 2s plus 1. I want to go on and do the multiplication of the denominator terms, so that will be tau 1 into tau 2 s squared, okay, plus tau 1s plus tau 2s plus 1. So that is my equation, which will be K1 into K2 over tau 1 into tau 2 s squared plus tau 1 plus tau 2 plus tau 2 into s plus 1. So this is the equation that I have, that I developed here. And what do we have here? Now we want to say that if I want to have, I'm going to have a stable process for this system here, and to study the stability of this process, okay, to study the stability of the process, so we are going to deal with the second order process, and we are going to introduce a step input for that. To study the stability of the process, what do we look at? We can look at the poles, they call them the poles, or let me say we look at the denominator now. You remember that when I said that if you have a denominator which is positive, and when we said that you have denominator which is positive, if you can remember, if I had 1 over s plus a, if you take the Laplace inverse, I'm going to have e to the power minus at. And what does that mean? It means that it is stable. Why? Because if t approaches infinity, this will decay, right? This will be decaying if t approaches infinity. And why? Because I have here a negative pole, they call it. Okay, they call it a negative pole. However, if I have something like 1 over s minus a, and I take the Laplace inverse of that, this will be e to the power at, and you can see this, if this will go to infinity, it will go to infinity if t approaches infinity. So e to the power infinity is infinity, and that is when I have a positive pole. Positive pole, that means if you find the zeros of S minus, so you're going to say, well, S minus A is equal to 0, and this means that S is equal to A. So that is a positive pole. And here we're going to say, well, S plus A is equal to 0. This means that S is equal to minus A, and that is a negative pole. Okay? So based on that concept that we have here, we are going to get to many ideas. So we are talking about stable of process. Number 2, we also can talk about the oscillatory nature of the process. Okay, so is the process oscillatory or not? Well, what do we mean by oscillatory? Oscillatory means something that looks like a sinusoidal wave. And when do we have a sinusoidal wave? If you can also recall, we will have a sinusoidal wave if you have the denominator or the poles have a complex root. So if you have a complex root, you're going to have an oscillatory process. Why? Because you're going to have a sine or cosine or both. Okay? Based on all what we have stated now, we need to work on this equation and find out what are the values of tau 1 and tau 2, which makes this system stable and which makes it oscillatory. And by that we can study the nature of that second order process. So I'm going to write the equation again. Okay, so that the answer was what? It was k1 over k1 multiplied by k2 divided by tau 1 tau 2 s squared plus tau 1 s plus tau 2 s, right? Tau 1 s plus tau 2 s plus 1. So that is what we have obtained in our equation here. Okay. So what we'll try to do here, we'll try to apply our the quadratic formula. I think they call it the quadratic formula. You remember the quadratic formula to solve whatever. Okay, it is equal to x is equal to minus b plus or minus b squared minus 4ac under the square root divided by 2a. So now I think you already remember that. So here for us, we are not talking about x, we are talking about s. Okay, we are talking about s. So solving that and substituting, what we will have s is equal to minus b. What is minus b here? Okay, so minus b here actually is tau 1 plus tau 2. And in this case, I think so we need to do some rearrangement of that equation there. We need to do some rearrangement which will make our system look much better. So we will try to put our system in the standard form that we have just stated, which is k over tau squared plus 2 xi tau s plus 1. And we'll see that how we can gain from that. So what is tau? Tau is the square root of tau 1 and tau 2. Okay, tau is equal to square root of tau 1 into tau 2. And what is xi? So we have 2 xi tau is equal to tau 1 plus tau 2. And our xi will be tau 1 plus tau 2 over 2. Okay, so what did I gain now? Please tell me what's going on here. Okay, now we will apply this quadratic formula on the basis of that standard form that we have here. Okay, and to apply from the standard form, so minus b now is minus 2 xi tau. Okay, so this will be minus, I think with the white this will be much better. So this is minus 2 xi tau plus or minus b square. So my b square here, okay, my b square here will be 4 xi square tau square minus 4ac, so it's minus 4 into a, which is in this case it is I forgot the s square, sorry, so it is tau square So my for a tau square, c is 1, so it will remain 1 like that. And this is divided by what? This is divided by 2a, and a was tau square, so this is divided by 2 tau square. Okay, so let's continue on with my problem. So what do I have here? I have 2 minus xi tau plus or minus, and I think I can take a common factor of 4 tau square here. And 4 tau square, to get out of that square root, it will be 2 tau. So that will be 2 tau, and I'm going to be left with xi square minus 1 divided by 2 tau square. So just continuing on that, this will be 2 tau can be cancelled out from here. So I'm going to have this 2 tau out, and the 2 tau out. And I think so my equation is neater now by minus xi plus or minus xi square minus 1. And this is divided by what? Divided by tau. And actually looking at the equation here, I think so we can do a good analysis of what we are trying to target here. And what is this analysis? The analysis says that when I'm going to have a complex root, when I'm going to have a complex root, I'm going to have a complex root in the case that xi square minus 1, okay, xi square minus 1, the term which is under the root is less than 0, right? And if the root is less than 0, so that will be like that. And then, of course, you're going to find the square root. So this will be like between minus 1 and 1. So what we are saying that we will get a complex root if it is from minus 1 to 1. And in other words, we are saying that it's not only you're going to get a complex root, it also means that a complex root means that it is oscillatory. So if xi is between minus 1 and 1, it will be oscillatory. So that is our first conclusion. That is our first conclusion. However, we need to consider something, that if xi is between 0, if xi is negative, in that case, if it is negative, what will happen? This term here will be positive. If xi is negative, this term here will be positive. And having a positive pole could be a problem. So if xi is negative, so we will say here that if xi, okay, if xi is negative, what you're going to have? You're going to have a positive pole. And having a positive pole, that means you're going to have an exponential of something that will never end, a positive t. So it means that will be not stable. Okay, this will be not stable. And I'll write that in blue. This will be not stable. Which means that I don't want to consider the negative terms. And not considering negative terms means I'm going to stick myself only from 0 to 1 to say that it is oscillatory. So we come to some conclusions here, that if xi is greater than 1, if xi is greater than 1, which means that if it is greater than 1 here, I will have a real root which is negative, that means it's stable. And both of them are be unequal roots, okay? Because it's going to be plus minus, plus a term and then a minus a term, right? So it will be two unequal roots. So I will have real and unequal roots, okay? And we call these roots as poles. So I'm going to have real and equal roots. And if xi is equal to greater than 1, I will have no complex roots, which means I will have the system is going to be not oscillatory. In other terms, we are going to learn a new term here, which we call it overdamped. Okay, so it's going to be overdamped. Okay, so that is my first conclusion within that table here. Okay, what other conclusion? Now, if Zai is equal to 1, it means that the square root will be square root of 1 minus 1, which is 0, and then I will have the answer is minus Zai over tau. So I will have real roots. However, these real roots are going to be equal, and we call this critically damped. And this just means the critically damped means it is a stage between an overdamped and the underdamped process, or it is a stage between being not oscillatory and oscillatory, and that's why they call it critical. That means it is at that point between oscillatory and non-oscillatory. So they call it critically damped, and it looks like the overdamped. And between 0 and 1, and between 0 and 1, what do we have? Between 0 and 1, we are going to have complex roots, or they call it the complex conjugates. And having these complex conjugates, I'm going to have a sine and a cosine wave, which means that it's going to be oscillatory, and the term that we are going to use here is underdamped. Okay, so when it is underdamped, it's underdamped if it's under 1. When it is overdamped, is overdamped when it's over 1. When it's critically damped, it's at 1, right? It's between the system where it's going to be not oscillatory and oscillatory. And this is our table here, how we obtained it. I know we have taken some time for that, but this explains what we have. This explains our slide here, where it says that type of behavior depends on the numerical value of the damping coefficient. So the Zai is called damping coefficient. Where does it come from? It comes from this standard format: k over tau square s square plus 2 Zai tau s plus 1. Okay, so one Zai is greater than 1, I am having an overdamped process, and the reason is that I have real roots which are negative. Okay, here real roots which are negative, I must say this, and they are not equal. Critically damped is just a stage between the two, and we have equal roots. Underdamped is between 0 and 1, and we are going to have complex conjugates. And complex conjugates, the real part is negative. I need to say that. So it's like, for example, minus 2 plus 5i. Okay, so the real part is still negative. Okay, the real part is negative to make it stable, to have it a stable process. Otherwise, we will have an oscillatory process which is not stable. Okay, so it does not mean that if it's less than 0 that it's not oscillatory. We already said that. If you look at our system here, we already said that between Zai is going to be oscillatory between minus 1 and 1, and these two systems, I'm just showing you that if it's from 0 to 1, okay, from 0 to 1 it is oscillatory, which does something like that. Okay, and that is Zai from 0 to 1, so it's oscillatory and it's stable as well, so that's why it goes down. However, if it is from minus 1 to 0, okay, so if it's from minus 1 to 0, this will be something that looks like that. So it is like that, and then oscillatory, and then oscillatory, and it goes on, right? So this is oscillatory and unstable, where we have negative terms, okay, and of course if we go more negative, it will just go like that. Exponential term, it will be like an exponential term that goes infinity, an exponential term going to infinity. So this is just explaining that we are considered about the real part of that conjugate is going to be negative, and this real is negative. Okay, so it must be like that. Okay, so what will the response look like? And this is the beauty of why we are trying to put it in a standard format, because once we put in a standard format, we know that we can study the action of the process of the second order. Okay, we can study the second order system. What is a second order system? We have taken an example of two tanks together, right? How does Ca2 get affected because of Fi? And now I can know how it will be affected by knowing the values of Xi. Okay, by knowing the values of Xi. And here, looking at the values of Xi, we already said that is going to be oscillatory if it's between 0 and 1. Okay, and which means that if as closer it goes to 0, it will be more oscillatory, and that's why it's at point 2 is very oscillatory. It has an high overshoot here, and it's less oscillatory here, and less oscillatory. So it's less oscillatory as we approach 1. Okay, so it's less oscillatory as we approach 1. When we reach 1 here, we can see that our system is what? We can see that our system is critically damped, and the higher you go than 1, you will have it overdamped, and overdamped is like a very slow process. It is a slow process, but it will never oscillate. But here it is a fast process, but it overshoots the steady state value that you're trying to reach, or that it is going to. So it overshoots and it goes down and so on till it decays because of the exponential terms. So what do we have here? The responses exhibiting oscillation and overshoot are obtained only when values are less than 1. So we already said that, right? So if it's less than 1, however, of course, it's greater than or equal to 0. The large values, of course, when you say 0, we do mean that you're going to get something that is continuously oscillating, and you can check that. Large value of Xi is a sluggish or a slow response, which is, we mean large values which are greater than 1, but the higher you go, it will be sluggish and slow. The fastest response without overshoot, and here the fastest, I don't like the word fastest here because it's not really the fastest response, but it doesn't have an overshoot. Okay, the fastest response without an overshoot. Of course, yes. The fastest response without the overshoot is obtained for the critically damped case for Xi is equal to 1. And now, after we had seen what will be the performance characteristics for the step input to an underdamped process. I know we did not take into the details of going through the step input and the partial decomposition, but this is a typical response of a step input to a process, to a second order process. However, in this case, we are saying that if Xi is between 0 and 1, we are going to get some response which looks like the one in front of you. And looking at the response that is in front of you here, we want to say that what is a good response and what is a bad response, okay? Or how you can say that the response is slow or fast, or what are the terminologies we can use to talk about our response. So in this case, we call them the performance characteristics. So what are our performance characteristics for the second order system as a result of a step input? Okay, so we are going to look at the rise time. Okay, so this is called the rise time, and the rise time is the first time it hits the set point. So if we say that because you have changed in your tank, that we said that you have like two tank system, right? And here's Ca2 and Ca1 and Fi. Because you changed Fi, Ca2 changed, for example, it changed from some 2.2 to 0.3 moles per liter, okay? So we are saying that it changed from 0.2 to 0.3. So if I would say, like, for example, this is like 0.2 and it changed to 0.3. But how did it change? Did it change in this manner here, or it changed as you can see it went up and then it went down and then it went up and then it went down and so on? So first thing we want to say here is that The rise time is the first time it hits the new steady state value that it will decay for at the end when t approaches infinity, or when you apply finite Wiley theorem to find that value. Okay, so if it goes like that, is it better or not? I know you may get confused and say, oh my god, I cannot say that if it's better or not. It's difficult. Why is it difficult? I know that the rise time here looks better, but I had a higher overshoot. Okay, I had a higher overshoot, so it jumped to a higher value, and sometimes jumping to higher value is not good. It is not good. And why it's not good? If I take another example, if I'm trying to have a temperature control, if my temperature jumps, for example, from 65, I want to get to a 70 degrees centigrade, and it happens that it jumped to a 75 degrees centigrade. Some processes, they as one of the processes I worked in my PhD, where I had a polymer to form, and why I was working on the polymer, as I approach 75, my polymer starts breaking down, so it was not at all advisable that I should pass even 72 degrees. So my target was 70, but I cannot overshoot over 72. So I may want to get fast from 65 to 70. I want to go from 65 to 70 and stop. But the faster you go, as you're running in a race, really running fast, you cannot just stop at the stop line. You need to get your momentum is still inside you, what we call in Arabic senna. Okay, so you still have it inside you, and you need to go and running very fast, and you jump up there. Okay, so you just cannot just stop at that stop line. Okay, so what I'm trying to say, it's better to have a lower rise time, so a small rise time, but if you have a smaller rise time, you will have a higher overshoot. So now we know what is the meaning of rise time. The rise time is the time that first hits the set point. Okay, so that is my rise time here. Okay, good. So what do we have else? Now we want to calculate. Now we want to know what do we mean by overshoot. Overshoot is that how much it shoots over the set point. Okay, and how do we calculate this? We calculate this by comparing A divided by B. Okay, so the overshoot is equal to A divided by B. How much it overshoots from the set point. So it jumps, it goes to the set point, and then it overshoots. Okay, so we calculate it as A divided by B. And the lower the overshoot is better. The lower the overshoot is better. So that is the explanation for the overshoot. Okay, let's go to the next. We already know what's time period. Time period is the period, this time between two excessive peaks, so that is easy. And what else do we have? We have the peak time. It is the time to reach the first peak. So this is my first peak, and that's the peak time. So I think so this is easy as well. What else do we have? So I think we finished all of them. We are left with the settling time. Okay, settling time. And what is the settling time equal to? The settling time is the time where the response enters a plus minus 5% of that steady state value. Okay, so here, for example, I'm trying to reach 70. Okay, I'm trying to reach 70. So if I'll normalize that, and putting it in a deviation format, so this is like going from 0 to 5, right? It's going from 0 to 5. Okay, so this is like from 0 to 5 degrees in a deviation format. So I will say that plus or minus 5% of 5. So what is plus or minus 5% of 5? I think it will be 4.95, and it will be 5.05. So this is the region the acceptable region, the region that if it enters and never goes out again, it is the region where it settles. Okay, it settles within those regions. So it settles. Okay, so it settles within this region that we have here. Okay, sorry for that. And talking about the settling, where it settles within those two regions and never goes up again. So let's remove this red line here and take and see how it settles. So it goes up, down, up. It went down, but it did not settle, right? Okay, it went out of that. It went out here. If you can see, if this is the straight line, it went out. And then it entered again within that plus minus 5%. And now when it entered, it did not go out again. Okay, so it settled inside that plus minus 5%. So what's the settling time? Is the time that it enters, the time that it enters and it never goes out again. So the time that it enters and never goes out again is the settling time. And here are the definitions that we have. The definitions say that the rise time is the time that's the first thing we explained, the first time it hits the peak, the time the process output takes to first reach the new steady state value. Okay, not the peak, sorry. It hits the new steady state value, the first time. And the time to the first peak is the time at the first peak. Okay, settling time is defined as the time required for the process output to reach and remain inside a band whose width equal to plus minus 5% of the change. And we will use plus minus 5%. Sometimes it's referred to as 2%, but we will use, I'm saying that we will use plus minus 5%. Overshoot is A over B, so how much it shoots over the set point divided by B. Decay ratio is C over A. I did not explain decay ratio, I forgot. Okay, I'm going to go back to this. The period of oscillation is the period, right? Between two successive peaks. So the time between two successive peaks. So looking at the decay ratio, the decay ratio is how is my new peak getting smaller in comparison to my previous peak. So if my peak gets smaller by 1 over 4, that's really great. So that this peak, here is 4 times smaller than the peak that I have here. Okay, so what I'm trying to say here, the decay ratio is equal to C divided by A. So the decay ratio is C divided by A. So it is this peak divided by that peak. Okay, and the smaller the decay ratio will be better, because it means that it is getting smaller faster than we are than the normal condition. Again, so if I have the decay ratio is equal to 1, okay, what does it mean? It means that this peak is equal to the previous peak, right? So it means that it's a continuous oscillation, and this is totally not good. Great. So this is what we have taken. What we have taken today is we have taken the step input to an integrating process, and then we have taken a step input to a second order process, and this was the explanation to a step input to a second order process. What we have left is the custom if inputs. Okay, so what we have left is the custom if inputs, and we are going to explain here the custom if inputs, and by that we are going to finish chapter 4. By that we are going to be finishing chapter 4. So here I'm going to explain the custom of inputs. And as I finish chapter 4, we need to solve now many problems so that we can catch up with all the things that we have studied, and then I can enter chapter 5 and 6. We will see how that goes. with solving problems. But let's start with the custom of inputs. And for the custom of inputs, okay, for the custom of inputs, there's something that I forgot to explain before I get into the custom of inputs, which is something also related to the second order processors. So where we have stopped is that with the rise time, time to first peak, settling time, overshoot, decay ratio, and we have explained the details of all that. And we have explained how we can obtain them from the figure. So what we are trying to say is that we can get what is the standard form, which is K. Okay, so we can get what's the standard form. I think I was explaining on a different one. Okay, yes. So we can get the standard form, and this is the standard form. We can get the values of K, Tau, and Xi, which means I can get my transfer function. I can find my transfer function by looking at this figure. Okay, so I can find my transfer function by looking at this figure. K is the change of output over the change of input. So this is going to be given in the problem. What was the change of the input and what was the change of the output? Change of the input, like we changed from 20 to 30%, so it's 10. And change of the output is my new steady state minus my old steady state. So it's this value, okay, B. So we can know that the change of the output is what? The change of the output is B. So we know that this delta Y is going to be B. So you see, like, we can get some information. We can get some information from the figure that we are looking at here. Just to have it bigger for you is easier. However, how to find Tau and how can I find Xi? Okay, how can I find Tau and how can I find Xi? So that I can find this transfer function. Well, the way of how you can find Xi and Tau, the way that how you can find Xi and Tau is by looking at what? By looking at some values of the overshoot. You know, the Tau is a constant, right? It is time. And since it is time, I can get the value of Tau by knowing either TR or TP or the time period, because all of these are time. So I can get Tau out of that. And then I can get the value of Xi. Maybe I can look at how the response looks like, and I'll try to find what is the value of Xi here, or how this response looks like, and I find how I can find the value of Xi. I know all what I have said, just made it more complicated, okay? I just made it more complicated. Please, doctor, can you have something simpler than that of how to find Tau and Xi? Yes, I can, definitely can. And where we can find that? If you go to your textbook, and if you go to your textbook, you're going to find a figure, which is 511, and you're going to find a group of equations. Either one you're going to find is good. And what we can see here in this table is that if you want to find the value of Xi, okay, if you want to find the values of Xi and Tau, the first thing you need to do, let me take this, maybe this is easier. Let me test that. If this works, it will be helpful for us, okay? So let's see, this is page 137. Okay, so please, I want 137. Okay, great. So I'm here, and then I'm going to use the pen because I couldn't use the pen in Google Chrome. Okay, so what I'm trying to say here, sorry for that. Okay, please, I don't want this. Okay, so what I'm trying to say here is that to find Xi and Tau, okay, I want to find Xi and Tau, these two values here. First, I need to find Xi, and then I need to find Tau, okay? Why? Because if you want to find Tau from any one of the things that has time here, like time to first peak, period, it will have, if I have TP from the figure, the time that it reaches first peak, I will have two unknowns, which is tau and xi here, right? So I will have two unknowns. If I have TP, I will have two unknowns, tau and xi. So I cannot solve it. So the first thing I should do is that I can find the overshoot or the decay ratio, either one. And if I have the overshoot, I'm going to substitute for the overshoot and find what? Find xi through trial and error. So we can find xi easily, okay? And after you find xi, what you need to do is substitute here. Oh my god, this is like a really big one, okay? So something like that will be better. So we are going to substitute xi here. And now when you substitute xi here and we have TP, we can find tau, okay? So it's as simple as that. And I think so now I just made it easier. So I can find the values of xi and tau first by finding xi through the overshoot, and then finding tau either by knowing the TP or the P. What I also want to mention is that if you don't want to use this, you can use the figure. The figure is another way of how to get what you want rather than going through the equations. And by looking at the figure here, okay, so I hope that is okay. You can see it. I hope that now you can see this. Okay, great. Now we are here. Okay, so what do I have here? What I have here is that if I know the overshoot, for example, the overshoot, here's the performance characteristic. So it's like this is the figure for decay ratio, overshoot, and 2 pi tau period. So what I mean is that if I'm talking about overshoot, so I'm talking about this line here only. Okay, so I'm talking about this line here only. So if I'm talking about decay ratio, I'm talking about this line only. If I'm talking about the period, I'm talking about this line only. Okay, and in this case, I'm talking about overshoot. So I'm saying that if the overshoot is 0.4, okay, so you go to performance characteristics. This is the line of the overshoot. So if it's 0.4, okay, that's 0.4. What is the value of xi? Xi is equal to 0.3. And if xi is equal to 0.3, you see, if xi is equal to 0.3, what will be the value of the 2 pi and so on? So that will be the value of the performance characteristics of what? Of 2 pi tau over period. And we have the time period and we can find the value of tau. Okay, so this is the way of how to either to use the figure, or if you want to use the equations. Okay, and now we have a methodology of how we can find tau and xi. Okay, so after we have done that, now we can talk freely about the custom of inputs so that we can finish up this chapter here. And I discovered that was chapter 5, by the way. So we are doing a very good progress here. So now the custom of inputs. We have taken many types of inputs. And one of the types of inputs was the pulse input. Okay, so we have taken the pulse input. And my pulse input was something like that. And we say that this is like a step input and another step input on the negative side. So this is a step input and then another step input. So that is my pulse. And we said that looks exactly like h over s into 1 minus e to the power t over tau. Okay, so this is what we have mentioned. Now, just to look more into it, into some different ways of how to write this one. I'm going to write for this this in the time domain and then in the s domain. So this is the time domain. How I'm going to write this function that I have in front of me here. So I'm going to write it in this way. So I need to put some numbers. It's always good to put some numbers because without numbers it just looks it looks more difficult. So if I have here 1 and 2 and I have a number like 2 and 4 here, okay? So what do I have here? So I have a step input of 2, okay? So I'll put that in blue. So this is like a step input of 2. When did it happen? It happened at 1, okay? It happened at 1 second. So here's 1 and this is 2, right? So what I have a step input which in the S domain, let me say that in the S domain, I don't know which one is easier for you to think of. So it's like a step input that happened at what? That happened at 1 second. Okay, so that is what happened here. Okay, that is what happened in this place here. Okay, if I want to write that in the time domain, this will be like a change from 2 to 4, so that is 2. And this 2 happened at what time? It happened at time t minus 1. So this is the way how we write that in the time domain. And I already mentioned that sometimes they put S, they use S in the textbook, or they use U. Whatever S or U, this means nothing except that it means that this happens at what time? It happens at 1 second. This 2 change happens at 1 second. So that's what it means exactly. And when you take the Laplace of 2, which is a constant, is 2 over S. And this is like a time delay that happens at 1 second, which is e to the power minus S. And we want to have another, minus 2. So we're going to have another minus 2 here. And this minus 2 is going to be minus 2 that happens at 2 seconds. And this is like minus 2 over S that happens at e to the power minus 2S. Did we finish? Actually, we did not finish because there was something tricky here. I just recognized that because you always need to start at 0. We always need to start at 0. And in this case, we are saying that there was another step input that happened at 0 that took it to 2. Okay? That was a step input that happened at 0 that took it to 2. Which means that we forgot something that we should have added. And this thing that we should have added was 2 that happened at ut minus 0. Okay? So I'm going to remove this. Okay? And I'm going to write the t domain here. Okay, so I'm going to remove this as well. I'm going to write the S domain here. And writing that, okay, sorry for this. And writing that this will be 2 happening at ut minus 0. Okay, that's ut minus 0, so it's just ut. And if you take this in the Laplace domain, this is like 2 over S, which is a step input. So yes, if you look at the S domain, there was a step input at 0, and there was another step input of 2 as well at 1 second, which is e to the power minus S, and there was a minus step input of 2 at 2 seconds, which is exactly like that one. In the time domain, there was a 2 change from 0 to 2 that happens at 0 seconds, which is ut minus 0, and there was another one happening at 1 second, which is ut minus 1, and which was a step of 2. And there was a negative step of 2, which is minus 2, that happens at 2 seconds, which is that 2 seconds here. Okay, so I hope that clarifies that custom of inputs that we are trying to see here. Well, if you want to draw another custom input just to make it more interesting, okay, and looking at it more interesting, for example, I have something that looks like that, and I'm going to draw it. Okay, something that looks like that, okay, I'm just creating something for you. And let's say that here it was 0, it was 1 here, it was 2 here, it was 3, and here it was 1 and 2 and 3. Okay, so now if I want to write this in the time domain, and then I want to write this in the S domain. And what I'm going to write in the time domain, I'm going to say that there was a step input at 0, there was a step input of 1, step input of 1 that happens at 0 time. So the step input of 1 that happens at what? E to the power minus 0s. And e to the power minus 0s is simply 1, so that we don't need to write that. And then there was another step input of 1 that happened where? That happened at 1. Okay, that happened at 1 second. Okay, so another step input of 1. I said step input of 1, like from 1 to 2, which is 2 minus 1. So it's a step input of 1 that happened at 1 second. Okay, and then another step input of 1 that happened at 2 seconds, and this is the one that happened at 2 seconds, and there is nothing happening, and then a step input that happens at 3, but this is like it goes from 3 to 1, so it's -2. So it's -2 and then nothing is happening. Okay, so this is -2 that happens at 3 seconds. Okay, that happens here. If you can see, that happens here at 3 seconds. It happens here, it goes down, and then nothing is happening. If you want to represent this, this is like happening at 0 seconds, and then I am having a step input that is happening at 1 second, and another step input that is happening at 2 seconds, and then a 2-step input, okay, of 2 units that is happening at 3 seconds. So this is like how we are going to write this in the time and the S domain. I know you have into your mind that, Doctor, you already gave us a step input to a first order. Will you give us a custom of input to a first order? The answer is no. Okay, we will concentrate on the step input, ramp input, and what we have taken, the sinusoidal input to a first order process. And mainly we're going to concentrate on the step and the ramp input and the impulse, not the sinusoidal. But we will not give you the custom if inputs to a first order process. But I'm giving you the custom input just to know that if you had one day later in another course a custom input, you know how to deal with that, and you know how to write it in the time domain and in the S domain. Okay, so we already studied not only the step input. Let me remind myself, we studied the impulse, the step, the ramp, and the pulse input. All these are very important, and sinusoidal is something that of course you should know, and you should know the effect, but we may not take examples that has direct relations with a sinusoidal input. Okay, so now we know this. Now we are going to take another example as well. So if we take an example here, and this example looks something like that, like that, like that. It goes down and then it goes straight again. Okay, so and here what do we have? We have something that is new. Okay, we have a step input, and we have a ramp input here, and we have a step input here, and this is what we have. How we are going to represent that in the T domain, and how we are going to represent that in the S domain. Okay, so that now we are going to start. Let us see how we are going to do this. I always need a breath for that kind of a question. So what do we have? First, we are having a step input because our 0 starts from here. So we have a step input here, and then we have a ramp input. My ramp input became a straight line. If my ramp input became a straight line, it just means what? It means that there was another ramp input that cancelled out the effect of this ramp input. And because it cancelled the effect, it became a straight line. And then there was a step input, and then nothing happened, right? There was a step input that brought it to this situation, then it was like a straight line. So the new thing that you're learning is that if you have a ramp, okay, so if you have a ramp and then you have a straight line or horizontal line, it means that there was another ramp that happened at the opposite, exactly the same amount, but in the opposite direction, which is just a negative term, which made it a straight line. Okay, how that will appear if I write it? First, my step input, I'm going to write my step input that happened at 0. It is a unit of 1. It goes from 0 to 1. So that is 1 over s at e to the power minus 0s. Okay, I'm going to write that, even though that I know that this is equal to 1. And then I had a ramp input. Okay, and this ramp input that I have here, this ramp input is 1 over s squared. If you remember, the ramp input is 1 over s squared. When did it happen? It happened at e to the power minus 1s. Okay, it happened at e to the power minus 1s. And then I had a ramp input at the opposite direction that happened at 2, that cancelled the effect. So I'm going to have minus 1 over s squared that happened at 2 seconds. Okay, here. And when it cancelled, it's going like that, like that, like that, like that. And at 3 seconds, we have a step input. We have a step input. At 3 seconds, we have a step input that rotated by 2 units from 3 to 1. Okay, so I have a step input that of 2 units that happen at 3 seconds. And this is the S domain. What will happen in the T domain? I'm just going to write it. So again, it was just 1 into U of T minus 0 plus a step input here, and my step input, okay, it looks like that I missed something here. I said that there was a ramp input here. What was the slope of that ramp? The slope of that ramp here is delta y over delta u, which is 3 minus 1 divided by 2 minus 1. So 3 minus 1 is 2 divided by 2 minus 1 is 1. So I'm going to write it here. The ramp was 3 minus 1 over 2 minus 1, which is 3 over 1, which is 3. So that was the ramp, right? So that was the A. You remember AT for ramp? So that is A. So here I'm going to write 3. Okay, look at what I'm writing. So it's 3 into T. That happened where? That happened at U T minus 2. However, my T, because it happened at 2 seconds, I'm going to write T minus 2. Okay? Because it happened at 2 seconds, I'm writing T minus 2. So it will be 3 into T minus 2 that happened at 2 seconds. This only means that it happened at 2 seconds. It's not an equation, like it's only like if you do some kind of modeling to say that if T is less than 2, don't count this because this did not happen yet. This only happened when I reached to this is the action that happened which made it go as a horizontal line. So I have a step input, and then I have a ramp input, and then I have another ramp input. Okay, I have another ramp input of the same amount. Did I say this is 3 minus 1, which is 2. So the slope is 2. I was just surprised. I said it is not 3. Okay, so what I have here, I'm just fixing out my slope. My slope was 2. Of course, it will be 2 here. So let's continue. This means that I have a slope with the opposite direction into T minus 2. Not T minus 2. Now the opposite direction. Okay. So you see that I'm making mistakes here, and it's like confusing you. The first slope happened at 1. The second cancelling slope happened at 2. Okay. So the one that happened at 1, which means here it should be the T minus 1. Okay. So it should be, I'm going to write this again. So it should be T minus 1. UT minus 1. Now it's correct. And then the cancelling slope which happened at 2 seconds, which is T minus 2, UT minus 2. Beautiful. And the end of it was just a step input of 2 units of a step input that happened where it happened at 3 seconds. So this is how to write it in the time domain, and then how to write that in the S domain. Okay. More examples of custom of inputs. Yes, we have more examples of custom of inputs. And this is another example of a custom of inputs in which we have something doing like that. Very strange. So this slope is exactly like that slope. And I'm going to write here just 0 and 1. And just considering that here we have 0 and just to fix up this is like that, like this. Okay. Okay. And this has happened at 1. So what do I have here? First, I will need to start at 0. This is starting at 0, and here it is starting at 0. So it's like it is starting at 0, but I have taken my x-axis to the top here. So it looks like my x-axis is like that. Okay. So just not to confuse you, if you are not suitable with that, you're not happy with it. So it exactly looks like what? It looks like that, okay? And this is 0. So it starts from 0. So what do I have here? I have a ramp. Okay, I have a ramp. So I'm going to write here the T domain and the S domain. And the question is going to be like in the exam, please write the function of the input here in terms of the time domain and in terms of S domain, and you're going to write it like that. Okay, so in the T domain or the S domain, which one you like? I'm going to write the S domain. I like the S domain, easier for me. I'm just going to fix the one here. I forgot to say that we had a 2 slope and I forgot to fix that. Okay, so we're back. So I have a slope here. What is my slope? What is my slope? So this is delta y over delta x, right? Delta y. So delta y is 1 and delta x is also 1. So the slope is 1. So this is 1 over s squared. 1 over s squared. So the S domain is here. So this is 1 over s squared. And what happened from here to here? This is not a straight line. It's like a step that takes the t either up or down. So it is a step input. And my step input will be minus, and the step input here is, it's not clear how much it went as a step. So let me say if this is 0.3, so it went a step of minus 0.7. So minus 0.7 over s. That happened when? It happened at 1 second. And actually, if you look at it, what happened here, I have a slope. It was brought down by a step, and then it continued its way. So the slope was not cancelled. The slope here was not cancelled. Okay. What happened for the slope? It was just shifted. It was just shifted. Okay, shifted by what? By a step. Shifted by a step, taking it up or down. In this case, it brought it 0.7 units down. So that was 0.7 over s into e to the power minus s. So that's all. That's the solution, because the continuous of that thing up is just the continuous of the slope, which was not cancelled. Okay, so I hope that you got the idea of it. In the time domain, how does that look like in the time domain? In the time domain, I'm going to have a slope of 1. And that is happening at a slope of 1, which is t, and it's happening at 0, so it's t minus 0. So it will remain the same. It's happening at the time of ut minus 0. And then I have just a step input, which is 0.7 units of a step input that happens at that happens at time 1. That happens at time 1. Okay, great. Am I left with one more example, or is it enough? Okay, or is it enough? I think so. It's good enough what I have taken, because I think I covered most of the ideas that we need to cover. And by this, I can say that we have done a good job today. We have taken today in this lecture pretty much of stuff. Okay, so we have studied the types of inputs last time for first order. What we have taken today is a step input to an integrating process, and we also have studied today a step input to a second order process, second order system. And after we had done that for a second order system, we got to know what is the standard form of a second order, and we studied that from the standard form, how to know when it is overdamped and when it is critically damped and when it is underdamped and then we had studied the performance characteristics. So we studied the performance characteristics of the second order, where we studied the overshoot and the decay ratio and the rising time and the settling time and the time period. And then we said that we already know the equations here, as either we use the equations or we can use the figure. And by using the figure or equations, I can know the performance characteristics, and also I can get back to find my standard form of the second order system. Okay, and last of things that we have taken after we have taken the step inputs and studied all those, we have taken the custom of inputs, and that was the final thing that we have taken today. It was a pretty long lecture, but I think so that it was very valuable. We have done a very good job today. So at the end, I would like to say thank you for the effort that you're adding in. You are putting a good effort, and I'm sure that you are doing really well in your study. We are going to solve many problems. We are going to solve like at least 10 problems in chapter 4, another 10 problems in chapter 3, another 10 problems in chapter 5. So we are going to solve very extensively many problems just to make sure that you understand. So all of this explanation with some examples, we are going to overwhelm you and take many examples so that you can understand. Hope for the best. Alhamdulillah Rabbil Alameen. Thank you very much and see you soon. Ma'as salama.